This PID mod didn't impress me at first. It was stable and predictable, but the variation in the puck was still around 80 degrees. So I tricked it. The result? Only 1.2 degrees of variation. That's the stability I get from my ECM Classic PID, a machine that costs 15 times more. In this video, I'll show you exactly how I installed it, how I fine-tuned it, what the real temperature tests revealed, and the hack that made all the difference. If you already have a PID in your Delonghi Stilosa and don't want to see the installation process, feel free to use the timestamps and jump to the temperature tests. Before you try this will void your warranty. This installation was done on the Delonghi Stilosa EC235 220 volts European version. Your wiring may differ and you will be working with mains voltage. If you're not confident, don't do it. Speaking of safety, unplug the machine, remove the drip tray and water tank. I also recommend taking photos or short videos during this assembly so you remember the sequence and where each screw and connector goes when it's time to reassemble everything. If you need help opening the machine, check my demo installation video at 1 minute and 54 seconds. Today, I'll go straight to the PID. Also, this Stilosa is not stock anymore. If yours is stock, your schematic should look like this. Take a screenshot if needed. I removed the Eco PCB and installed a new power button. That's optional, but the Eco timer interrupts preheating and annoys me. I also have a dimmer installed for flow control and soft pre-infusion. The updated electrical diagram is on screen for your reference. Now we'll add the PID, the thermocouple and the SSR following this schematic. In the description, you will find a list of all components and tools required for this mod with affiliate links. I receive a small commission. You don't pay anything more if you buy from my links, you support the channel, but of course, feel free to buy anywhere else, no hard feelings. After opening the machine, you will see two thermostats. Steam thermostat on the upper side, brew thermostat closer to the pump. You may use the PID for steaming, switching the temperature to 140 degrees, but in this installation, we'll keep the steam thermostat. Then, remove the connectors from the brew thermostat. Unscrew the nut holding the metal bracket that keeps both thermostats in place. There was enough thermal paste, and mine is a 4-month-old machine, so I didn't add more. If the thermal paste in yours is dry, consider removing and reapplying. I'll leave a link in the description if you don't know which one to buy. I inserted the thermocouple between the thermostat and the boiler, then tightened everything back in place. This is the advantage of the hole washer model. It fits better between the boiler and the thermostat. Now the wiring. I cut 2 blue wires long enough to reach the SSR at the bottom, leaving some extra length, about 10 centimeters, and crimped male spade connectors on one end. One connected easily, the other was too tight. I replaced the connector and crimped a new female spade, connected to the other blue wire, and sent both blue wires to the AC terminals 1 and 2 on the SSR. Next, the yellow and green wires connect the PID to the DC side of the SSR. Green goes to terminal 4, the negative, yellow to terminal 3, the positive. I didn't have 4 connectors, so I looped the stripped wires under the screws. For placement, I fixed the SSR under the pump using double-sided tape, circa 1 cm from the back edge and 2 cm from the side where the power button is located. Under the vent would be better, I know, but the lid wouldn't close. Remember to avoid bending hoses. Water flow must remain unobstructed. Before closing the button, I reused T5, previously disconnected from the Eco PCB, to power the PID. For that, I took another blue wire from the top and crimped a male spade connected to T5. Now you can put the bottom cover back to work with more freedom and avoid accidentally disconnecting one or another wire in the SSR. The second phase that will power the PID comes from the rotary knob. Looking from the back, I removed the bottom left connector with a blue wire and used the piggyback connector to add this black wire. Then I reorganized the cables, measured and trimmed to length. For cable exit, I drilled a hole in the top cover in the center of this area to the left of the water tank. I started with a soldering iron, but you can use a small drill bit for plastic or wood, then expand with larger bits. 8 or 9 millimeters is ideal. I didn't have one, then I finished with scissors. Feed the thermocouple first, then the 4 wires, and reassemble the machine. Before mounting the PID, take a photo of the pinout. It's a standard, but different models may have slightly different connections. Always double check. In my case, I used a double-sided foam tape. It's easier to remove, and I'll probably install a gadget mate in the future. But you can use those silicone versions, heat-resistant, for better adhesion. Now connect the blue and black wires to 1 and 2, green to the 4, and yellow to the 5, thermocouple blue to 9, red to 10. Remember that terminals 1 and 2 carry mains voltage, so insulate them properly. I hope the installation was as easy as possible. Let me know in the comments if anything needs more clarification, and with that, let's move on to the tests. If nothing trips when you power it on, that's a good sign. First, set a low target temperature, 0 or 10 degrees, so the heater doesn't activate while configuring. Hold set for 2 seconds, adjust with arrows, hold set again to confirm. Now press and hold set to enter the settings menu. In mine, ARU is 0, 1 will enter in auto tune mode, P I set to 30, I to 360, D to 15, AR to 100, R to 1, meaning 1 second sampling rate. SC is the offset, the difference between boiler and puck temperature. To measure offset, I place the thermocouple in the puck with real coffee, dialed for 40 grams in 20 to 25 seconds. After 5 seconds of extraction, that's the starting puck temperature. If you want to run similar tests, I will left the links to the thermocouple and affordable thermometers are used in the description. With the PID set to 90 degrees and the puck reading 80, the offset would be -10. In this Stilosa, the offset was -2. LCK remains 0, press and hold set again to leave the settings menu. Now set your brew temperature. Mine is 90 degrees. With these parameters, it reached the 90 degrees in 4 minutes and 5 seconds with no overshoot. If yours is within plus or minus 3 degrees, that's fine. I'm just a bit obsessive. I also measured the recovery for back-to-back shots. It took 1 minute and 3 seconds to be ready again. To finish, I also recommend testing if the steam thermostat is limiting the temperature. It's another layer of protection. Set the temperature to 150 degrees. The steam thermostat should cut the power around 140 and you will see the temperature going down. Test the steam mode as well. Set the PID at 90 degrees, switch to steam mode and check if temperature is cycling around 130, 140 degrees, meaning that the thermostat is in control, not the PID. After steaming, always refill the boiler. Open steam valve in brew mode until water flows from the wand. Then close and ensure water flows from the group. Never let the heating element run dry. Now the real test. In standard set and forget mode, 5 seconds after starting the extraction, I measured 91.4 degrees in the puck. At the end of the shot, 83 degrees. That's an 8.4 degrees drop with a PID installed. That's not what I expected. I wanted more stability, not just a digital thermometer. So I started looking closer. The thermocouple position in the boiler doesn't see fast changes in real time. This stainless steel boiler retains heat very well, and its thermal conductivity is lower than aluminum. There's a noticeable lag. The PID reacts, but it reacts late. And that's when I asked myself, what if I could make it react before the temperature drop actually happened? Not by changing the PID parameters, not by moving the probe, but by changing how I use it. Right before brewing, instead of leaving it at 90 degrees, I temporarily increased the set temperature. I tested +5, +10, and +20. With a 20 degrees increase, 5 seconds into the shot I measured 90.2 degrees in the puck, and from there it was almost flat. Maximum variation 1.2 degrees. That's not a small improvement. That's the kind of stability I get from my ECM Classica PID, a machine that costs 15 times more. And I repeated the test. The difference wasn't random. The cups were more controllable, more consistent, and better balanced. Is it extra work? Yes, it takes a few seconds to adjust the temperature before and after the shot, but the difference in stability is measurable and significant. And that's when I realized something important. This little machine wasn't the limitation. I was. As always, don't trust me, don't trust the specialists, test it yourself. If you've measured bigger drops than you would like, even on other machines with a PID, try the +10 or +20 approach and see what happens. You might be surprised. And let me know how it goes in the comments. If this video helped you understand your machine better, consider subscribing. I have more experiments, tests, and practical hacks coming soon. Thanks for watching and see you in the next video. Ciao!